So the gross anatomy of the heart is such. We talk about the heart's position within the thoracic cavity and within the mediastinum itself. And we talk about the four chambers of the heart and some of the details there. But in a general sense, the gross anatomy of the heart includes the idea of the three layers of the heart, the three layers of heart walls. Now, when we look at the heart walls, we're really going to be concentrating on that myocardium, which makes up the bulk of the heart wall. When we slice open the myocardium and look inside of there, it looks somewhat like this, the picture on the left here. This is our typical picture of the microanatomy of heart cells, cardiac muscle fibers. As you can see, some of the features that you'll see here, if you look closely, you will see that they are striated or striped, just the same as the skeletal muscle fibers are striated or striped like that. And so they have the same kind of thing going on. They have the Z discs, the A bands, the I bands, all that kind of stuff. Inside of your cardiac muscle fibers, you will find many mitochondria. You'll find one or two large pale nuclei inside of each cell. One of the features, so a lot of these things are very similar, so you can see tons of mitochondria inside of there. Some of these things are very similar to skeletal muscle fibers, and in fact, all the things that pertain to the microanatomy of skeletal muscle fibers, for the most part, also pertain to the microanatomy of cardiac muscle fibers. So you have the sarcomere here, the T-tubule, the sarcoplasmic reticulum, calcium release, all those things are going to be working the same. One of the features that's different from skeletal muscle fibers is that these guys have these structures called intercalated discs. It's one of the ways that we can easily distinguish them from each other. And the intercalated discs, let's take a closer look at there. There's two things inside of the intercalated discs that are of interest to us. There are desmosomes. Desmosomes are little proteins that act sort of like hooks to actually hook neighboring cells together so that they're quite closely compacted together and quite closely packed together, and they hook together sort of like Velcro. And so these are the desmosomes. And separate from that, there are gap junctions. Gap junctions are basically, they represent the continuity of cytoplasm from one cell to the next. It's actually a pore that extends between cells. The gap junctions, what's most important about the gap junctions is that it allows for fast cell-to-cell communication. And the most important thing about desmosomes is that they prevent the separation of the cells. I want you to, this is a pretty good example of the separation of function and structure. You want to make sure that you understand the function of something. The function is a thing, and the function is an action. So I want you to understand what gap junctions are, but then separately what they do. And desmosomes, what are they, and separately what they do. All right, so taking a look at this then, the microanatomy leads to microphysiology, and the idea of the way that these things work. The way that these things work is very, very similar to the functionality of a skeletal muscle fiber. So I'm kind of emphasizing here function versus structure. And so when we talk about the function of, when we talk about the structure of these guys, the A bands, the I bands, the Z discs, the sarcoplasmic reticulum, the sarcomere, the sarcolemma, all of these things, as I said, are very similar to what happens inside of the skeletal muscle fiber. Also, all of the microphysiology works pretty much the same as well. So make sure that you understand that at least in terms of contractile muscle fibers, everything basically pertains just the same way. So you might want to go back and review your skeletal muscle physiology, especially if you're a little bit shaky on this particular topic, because I think it's rather important to understand the similarities between the two types of cells and then some of the distinctive differences as well. So some of the similarities here would be that with these contractile muscle fibers of the heart, the influx of sodium initiates a depolarization, which leads to an action potential. The transmission of the depolarization causes the sarcoplasmic reticulum to release calcium internally. The calcium then interacts with, the troponin, which you'll find on the thin filaments here. So all of the elements of excitation contraction coupling are still here, and we're still dependent on calcium, and we're still dependent on ATP for that cross bridge cycling. And if you don't know the words excitation contraction coupling and cross bridge cycling, like, those should sound familiar to you. And if they're not familiar to you at all, I will be happy to make some extra information available to you. You should probably just be able to watch a couple of YouTube videos just to refresh your memory, because they should definitely be things that you learned in the first semester of this class. If not, I personally think it's quite important to know them. And it helps then when you look at figures like this sort of a thing here, or this sort of a thing here. It helps to know what's happening at a microphysiological level so that you can put those kind of thoughts together and then be able to understand what we're talking about going forward. So taking a look at this, I just want to concentrate on one of these guys here. I think this is the one that shows this the best. Yes, this is the one that shows this particular phenomenon the best. What we're looking at here, and I'll take you through this figure more carefully during class, but what I want to point out to you is what we call a plateau potential. This particular shape is distinct, and it's called a plateau because it has a rather flat top there. There's another plateau potential shown here, but it's not quite as distinctive. This plateau potential, you can see that it's a very long potential. It lasts quite a long time. We'll talk about why that is. But what actually regulates this is what we call slow calcium channels. So the depolarization of the contractile muscle fibers is called a plateau potential. It is regulated, the depolarization phase is regulated through sodium channels, voltage-gated sodium channels, as you would expect. And the prolongation of the potential, though, is caused by calcium surging inward through slow calcium channels. So it basically prolongs the depolarization of these guys. The tension in a muscle can last 200 milliseconds or more, which is a very long period of time. That's a fifth of a second. In physiological terms, that's an eternity. That's a long time. So this allows for you to provide a sustained, long muscle contraction. So that's a plateau potential. We'll be exploring it more in class. And we're going to be comparing, just so you know, there's 3 different types of potentials that we're going to explore in class. 2 of them we're going to be discussing with relevance to the cardiac system, and 1 of them we're just going to be reviewing from what we did last semester. So the 3 types of potentials we're going to be looking at are called action potentials. That's a neuron situation. We're also going to be looking at the plateau potential, as I'm showing you here, and then the other one we're going to be looking at is called a pacemaker potential. I guess the last thing that I wanted to say about all of this is that when we talk about these cells here, these are called cardiac muscle fibers, contractile muscle fibers, etc. These take up 99% of the space in that myocardium. So in the myocardium, 99% of the cells, almost all of the cells that you find in here are contractile muscle fibers. The heart is a big old muscle, and that's what it does. It contracts hard, it contracts for a long time. The plateau potential allows that to happen. And just so you know, 1% of the cells that we look at here, 1% of the cells are called autorhythmic cells. They are also called cardiac pacemaker cells.